Good.
Thank you. Yeah, so I'm going to talk about what it means for an outbreak to be large and how do we predict this probability that it might be. So first of all, what do I mean by epidemic risk? So this is just an arbitrary pathogen which we're running simulations for, and here I think I've run about 1,000 simulations for this arbitrary pathogen, and we've initialized it with one infectious individual at the start, and then let the simulation run. And you can sort of see there are two modes here. One when the outbreak doesn't kind of take off at all, and another where quite a large proportion of the people, there's 1,000 people here, get infected by the end. And so it's pretty clear this upper mode will be considered a large outbreak, and this smaller mode will be considered kind of an outbreak that's fizzled out or a minor outbreak. So in this case, about 30% of the simulations occur in this upper kind of mode. We'll come backwards. So here I'm going to introduce two notions of epidemic risk, or the proportion of outbreaks which are large. First of all is the instantaneous epidemic risk. This sort of implicitly assumes that whatever your transmission conditions were when your infection was imported into your population, they remain like that until your outbreak's over. This is compared to the case epidemic risk, which accounts for changing transmission conditions after the infection first comes into your population. So in this example here, I've got a plot of mosquito population density, and there is maybe some kind of catastrophic event at t equals 5 where all the mosquitoes die out. And let's assume that we introduce a case just before this kind of die out. If we were to use the IER, we sort of assume that this remains constant along here, so we remain constant at 1 kind of mosquito per meter square. And so if we feed that mosquito population density into the IER calculation, we'd get a positive epidemic risk. However, if you use the case epidemic risk for CER, you're actually accounting for the fact that you get this sudden drop off. And so you really expect a zero risk. There's no way that, you know, a mosquito would bite a human and then that mosquito becomes infectious and then that mosquito bites another human in such a way that you get a massive outbreak in that tiny amount of time there. So the IER is quite simple. It's a solution to a system of outbreak equations, and the CER is more complicated. It's a solution to a system of ODEs. So for an SIR model, these two quantities are quite well known. You might have seen the derivation of the IER. In this case, it's 1 minus 1 over R naught. And then for the CER, it's got this kind of messy expression. I gave a similar seminar in Bristol, and someone said they thought this was beautiful, this expression equation. So I'm not going to kind of leave any judgments about what this looks like, but I don't think it's very nice. It's just kind of you need to solve a bunch of integrals. So simple versus complicated, but maybe useful versus useless if you've got very drastically changing transmission conditions. So this is an SIR model where we've got the transmission beta is changing according to this COS curve. So transmission peaks at about 15 units at t equals 0, and then dips at 5 at t equals 6. So I think probably it makes sense to talk about this in terms of like time units and months. And so if we consider an infection being introduced when transmission is high, such as there, and run the simulations, we get a lot of individuals in this kind of upper mode, and so we get quite a large amount of large outbreaks. But if we introduce infections when transmission is low, most outbreaks tend to be minor. And so let's compute the IER and the CER in this scenario. The IER, so assuming things are constant, we get sort of a nice symmetric curve. Just plugging this kind of 1 minus 1 over R naught from that beta and that mu into your equation. And you can also compute the CER by kind of solving all those integrals and plotting it. And the most interesting thing here is there is something called the winter is coming effect on the far left of the plot, where the blue CER is below the orange dotted IER, because the CER sort of looks ahead into the future and sees that transmissibility is going to get lower in the future, and so it accounts for that. And there's also perhaps a less catchy thing, which like which summer is coming, where the CER is greater than the IER because it looks ahead and sees that transmission increases in the future. And so the left plots were just theoretical, and the right ones are plotting the CER using that analytic calculation and running simulations, and so you can see those match quite well. Now suppose we were to change the speed of the outbreak. If your outbreak happens very, very quickly, And so maybe it's just focused on like a tiny, tiny proportion of the x-axis. We'd expect the match between the IER and the CER to be quite good. However, if the outbreak is very, very slow, then the whole amount of seasonality will make a drastic difference. And so here sigma is a sort of outbreak speed, where sigma is low, you get a slow outbreak, and if sigma is high, you get a fast outbreak. And you can see that as you increase sigma, we get a better and better match between the IER and the CER. And in fact, as sigma tends to infinity, the IER or the CER will approach the IER, because in that case, sort of seasonality is irrelevant, because all of your transmission happens in kind of an instance, which obviously isn't realistic, but it kind of is nice to see. So this is bad science communication, because I just dumped a bunch of maths on the board. But the left-hand side is a Ross McDonald model for vector-borne diseases. We've got susceptible humans labelled as S, exposed humans labelled as E, and infectious humans labelled as I, and recovered humans labelled as R. And we've got a similar thing happening with vectors, but we assume that vectors don't recover and they remain kind of infectious or infected for life. And so we've only got a susceptible, exposed, and an infectious class for the mosquitoes. And there's a lot of kind of complicated parameters like bite rate and things in there, but all these parameter values are taken to be kind of approximate Zika virus. So from this, you can derive something called the Kolmogorov equations, where if we denote P, I, J, K, L at some time t as the probability that a major outbreak happens, given that you've got I initial exposed hosts, J initial infectious hosts, K initial exposed vectors, and L initial infectious vectors, you can derive these ODEs which describe how this P changes, and these are Kolmogorov equations. And these are very, very difficult to solve in general. So what we've done, which is kind of the most novel part of this work, is conclude that you should probably use periodic boundary conditions to solve this. So the idea is that if you've got some sort of seasonality that repeats each year, your CER should be the same at some time t as it is at the time t plus 365 days or 12 months. And so you can solve this system with periodic boundary conditions just by setting all these p's at time 0 equal to the p's at time 12, so things repeat nicely in time. And the CER is going to be the P with one initial infectious person, so P0100, so that's what we're going to plot. We're going to use a case study, which is for Miami in 2018. On the top left is a plot of mosquito lifespan or mortality rate versus temperature. And this comes from Yang et al., where they basically take lab experiments and kind of torture mosquitoes by changing the temperature and seeing what happens. You can see it's sort of bimodal, where the mosquitoes kind of peak at 15 and around 30 degrees. And this is Aedes albopictus, I think. I always get confused which mosquito I'm working on at any given time. There's too many. So that's figure A. And then figure B is temperature data for Miami. This is just taking monthly average temperature data, and then we fit a cost curve to this data. The reason we fit a cost curve is because we want to reinforce that we've got periodic boundary conditions. And so putting in just the raw temperature data means you don't have periodicity, and so we fit it to a cost curve. Plot C shows how the mortality and the lifespan of the mosquito varies throughout the year in Miami or across the 2 years. And then finally, panel D, we plot the IER and the CER. And they're different, which means that seasonality must be important. And this suggests that we should use the CER because the CER accounts for seasonality. And again, you can see this summer is coming and winter is coming effect. With some simulations on plot show that the CER really is kind of accurate. And so you can do this for historic climate change over the Florida region. So here I've got historic data that averages over the periods 1961 to 1990, and then a similar data which averages over 1991 to 2020. So we've got two kind of temperature data sets. One is kind of early on, 60s to 90s, and the other one's a bit later on, kind of 90s to up until quite recent, for each different pixel around the Florida region. We can compute the CER for both cases, and then we just plot the proportion of the year for which the CER exceeds some chosen threshold. And I've just picked a nice threshold so you can actually see what happens in the graph here. But you can see, I'm always talking about forward spread when it comes to climate change and mosquitoes, but you can see this kind of northward spread up into Florida, where things are getting a bit hotter as the mosquitoes are able to kind of propagate disease better. And similarly, things seem to be getting a bit hotter. You can see a bit of Cuba there. So this is interesting. So now we're going to look at kind of climate change into the future. So to do that, we need to model how the Earth will actually change in the future and how the kind of relative concentration pathways or the amount of CO2 in the air will change. And to do this, there's a good framework called the shared socioeconomic pathways, which describe how countries might interact with one another going into the future and what kind of technologies we might use, and then the impact of those relationships into the amount of CO2 that we produce into the air. And so here's a graph of kind of year versus the amount of CO2 for different scenarios. SSP1 is kind of the best scenario where everyone is really keen on sustainability. We use lots of green energy and massively decrease the CO2 in the future. SSP2 is kind of an okay output. It's kind of the best we can maybe think of at the moment, going on a current trajectory where countries start to work together a bit more and we're a bit more green. SSP3 is a slightly worse case. This is regional rivalry. So countries are competitive over resources and are increasingly kind of carbon-based. SSP4 is inequality, where kind of inequality across countries and within countries is quite extreme. And then finally, there's SSP5, which is, although countries work together quite well, there's a lot of kind of use of carbon, the fossil fuels and things like that. And so the data we use is from the Carbon Model Intercomparison Project, or CMIP6, which just takes a load of different climate models and compares them and makes kind of a big document with all the kind of future scenarios that could happen. And so this is for SSP1, just for Miami, kind of averaging over several years. And so you can see the CER peaks around 6 months, and then it just gradually gets kind of higher and higher as we move through and the climate changes. SSP2, you start to see some bimodality in 2081 to 2100. And this is just because the temperature gets so hot, the mosquitoes start to kind of die around the summer times and can't transmit the disease anymore. And so we get kind of two modes. Again, this going forward to SSP3, things are getting too hot for mosquitoes in 2081 to 2100. And then finally, the worst kind of case is SSP5, where, I mean, this is sort of, I think, a bad message because it sort of says climate change is going to be fine. We get less disease, but you're going to have to remember that if things are too hot for mosquitoes in this sort of region, then they're definitely going to be too hot for us. And so there are other concerns, sort of immigration away from the area would have to be considered. So this isn't good news. We're going to consider an extension of this where we allow the mosquito populations to vary in time. At the moment, we're just considering a fixed population. So I was a bit hand-wavy when I talked about the notion of a major outbreak before. I talked about kind of running simulations and some of them getting big and some of them small. So the real way this works is you use a branching process model, which is, say I'm infectious at time 1 and I give Nathan an infection or something. I then reproduce into 2 people, one of which is infectious and one of which is susceptible, in such a way that the number of susceptibles never decreases. And this is a very good approximation right at the start of an epidemic when we've got exponential growth. But as soon as you get out of that exponential growth phase, this approximation becomes quite poor. And so in this way, the number of infections either remains finite and the disease dies out, or it shoots off to infinity because the susceptibles don't decrease. So if you imagine we have R0 that looks like this, where it's just above 1, we have sustained transmission early on in the year, but then there's no suitability for pathogen a bit later on. And imagine we introduce the pathogen at time 0. It'll be able to transmit for a bit, but then as soon as we get to R0 less than 1, and certainly when we get to R0 equals 0, the pathogen's going to completely die out, which means that this branching process never has a chance to go to infinity. And so if we were to use a branching process model, the output would be that the risk is always 0, because no matter when you introduce pathogen in this case, it's always going to die out, because it's never going to be able to go to infinity. But clearly there's quite a few months where R0 is greater than 1, and even greater than 0, which means you might expect quite large outbreaks. So for example, if you had Ebola, and this is how it looked, you might get like 3 or 4 infections. That would still be considered a large Ebola outbreak in certain countries. And so you kind of need to account for this. So here we introduce the notion of a threshold epidemic risk. And so this is the probability that the total number of infections exceeds some given threshold. So to do this, we introduce a probability Q with some threshold big T, and then some I star and R star infections and recovered at time T. So this is the probability that the final size of the outbreaks exceeds that threshold big T by some time, which we choose way into the future, such that the outbreak is assumed to be over by then. given that you start off, so you have I-star infectious individuals and R-star recovered individuals at time t. So in proper maths is given by that equation there, it's just a probability of exceeding some threshold. And there's some more bad science communication here, just kind of dumping equations on the screen. But essentially they're the same equations as before, but we don't let delta t, it's the time between events, go to 0. So this is like a discrete common law equation. And the other thing here is we use a boundary condition, which is given by that. So the probability of exceeding the threshold, given that you've got I-star and R-star infections and recovered by this time t max, which is after the end of the outbreak, should be equal to 1 if your number of infections and recovered is already above that threshold by that time. And it should be 0 if your number of infections plus recovered is less than that threshold by that time, because we're assuming that we're not generating any more infections by that time. And so whatever's happened has already happened. And so you can kind of apply these boundary conditions at the end. And so using those boundary conditions at time t max, you can work backwards to work out the TER. And so here we've got the same scenario as before. We've got some arbitrary pathogen, and transmission varies according to this beta. But here I just let beta naught vary between 1 and 11. So in figure F down there, R naught is greater than 1 for the whole year. And so the CER is quite a good approximation because there's actually no chance for the infections to die out. But then as soon as we allow transmission or R naught to decay to being less than 1, we start to see a discrepancy between the CER and the TER. And this discrepancy gets pretty large in figure C, where about half the year R naught is greater than 1, about half the year is less than 1. According to the CER, we get very, very few major outbreaks, just because most of them will die off before reaching infinity, and the TER remains quite large. So we were applying this in northeast Italy. We got some temperature data from a town called Feltre in 2014 and 2015. And again, we're fitting a cost curve to this because we want to enforce periodic boundary conditions, because we want to compute the CER to compare against the TER. And we feed this temperature data into a mosquito population model where different parameters within the model depend on temperature. So for example, on the top left, there's development rate from eggs to adults, so eggs to larvae, and then on the top right, there's development rate from larvae to pupae. And all these rates within the model are temperature dependent. So we can feed temperature data in and get mosquito population out. And it looks how you'd roughly expect it to in kind of northeast Italy, where mosquitoes peak in the summer. And because 2015 was a bit of a warmer year than 2014, we see kind of quite a few more mosquitoes in the right-hand side versus the left-hand side. And so we can use this to compute the TR, which we do by simulation, because the kind of analytic results I used before don't quite work in the case for mosquito disease. And we see that the CER and the TR is quite a large mismatch. And this is just because the number of vectors drops to basically 0. And so if we were to use the branching process, the infection would die out before it kind of reaches infinite infections. So yeah, there's substantial risk of seeing, this is for chikungunya, a chikungunya outbreak. And there's various different thresholds. So the probability of kind of exceeding five final infections plus recovered is kind of 0.25-ish at the peak in 2014 and 0.5 at the peak in 2015. The point here is the CER and TER are different, and the TER provides kind of more meaningful guess of what the outbreak probability would be. And we're doing this in Crete for a similar kind of model, but this time we're doing it over a large array of pixels, so 250 by 250 meters pixels over Chania in Greece. So this is quite a large area. And we're doing this for chikungunya, Zika, and dengue in the years 2017 and 2018. This is a plot for dengue, where we're looking at the IER versus the TER. And the TER is very jaggedy. And the reason for this is because lots of things in the dengue transmission cycle are dependent on temperature. And so we see kind of a very stochastic looking graph. And using the TER kind of smooths this out a bit. I mean, it's not clear that it is smooth because we're only sampling at like 5 points. But if you increase the sample, you get kind of a smoother curve. And what we're saying is you should use the TER compared to the IER because, again, you've got this sort of winter is coming effect kind of around here, I guess, and then a summer is coming effect around here. And this is more representative of how the pathogen will be transmitted in the real world. So yeah, the conclusions are, I've sort of introduced 3 notions of epidemic risk and told you that like they're all rubbish in certain scenarios. But you should definitely use the IR if there's no seasonality or your pathogen is transmitted quickly or seasonality is limited. And you should use the CER when sustained transmission is possible throughout the year or most of the year. And you should use the TER when the others fail. The TER is also quite useful for kind of people in healthcare because they decide what constitutes a major outbreak. So I was talking about Ebola before, maybe 4 cases of Ebola would be large, but 100 cases of COVID would be considered a large outbreak. And so this is quite useful for people in healthcare when they're deciding exactly what probabilities they should be looking at. Yeah, thank you very much.